Welcome to physics. Today I'm going to show you another example of horizontal projectile motion. Remember the hypothesis. Some 400 years ago, Italian scientist 26-year-old Galileo 1590 hypothesized that horizontal projectile motion, the time takes for horizontal projectile motion fall is the same as if you drop the ball. To give you an example to help you understand what I mean is this. A ball is rolling. Imagine a ball is rolling on a table, and at the edge of the table ball falls, and eventually ball falls and land on the ground. It takes exactly the same amount of time if you drop the ball from the same height. That's the hypothesis. This is going to be third example, and hopefully this will help you understand every angle of horizontal projectile motion. Okay, so let's dive into the problem. I'm going to call it Tom Cruise problem. Tom Cruise problem. As an actor, Tom Cruise needs to know how fast he has to jump off so that he can land at the camera. So here's Tom Cruise. He is 50 meter above the ground, and the range is, let's say, I don't know, the range is from here to the camera. From here to the camera is, let's say, 90 meters. What do we want to know? How fast Tom Cruise has to jump off so that he can land at the camera. So we want to know this. We want to know initial velocity has two components, vi x and vi y. We want to know vi x. We don't know it. We want to know. We know vi y. What I mean at location 1, let's say this is location 1. At location 1 velocity, this is the initial velocity. Alright, we start measurement. We start our stopwatch from right here at this location, at the edge of the cliff. That's where we start measuring the time. At the right here, velocity has two components, vix and viy. Viy right here is 0. So to find the elapsed time, we have to use dy is equal to vit plus half at square. So at the y direction is negative 50 is equal to viy is 0, half minus 9.8 t square. So minus 50 is equal to 9.8 times 2 is negative 4.9 t square. Negative cancel, so t square is 50 over 4.9. So elapsed time is 3.19. Okay, so the time at location 2, just before Tom Cruise hit the ground, the time is 3.19. Okay, well, we want to find the initial velocity right here. So we can use the other component of this equation. What is the other component of this equation? So I'm going to write d is equal to vat plus half at square. Since we want to find the x component of the velocity, we have to use the x component of this formula. Acceleration due to gravity at x direction is 0. So now what survive is dx is equal to vixt. So dx, we already have that, 90. Vix is something we want to find, and t, we have that. Right here, when he about to land the ground, or when he is almost at the ground, the time is 3.19. So Vix is equal to 90 over 3.19. So 90 divided by 3.19 is 28.21. Vix is 28.2. So 28.2. All right. So this right here, Vix is 28.2. The velocity at x direction remain constant. Velocity at x direction remain constant. What do I mean? Let's use the different color. Right here Vx is 28.2. 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 Never changes because acceleration due to gravity at the x direction is 0. Right here the velocity at the y direction is, alright, so forget about everything else now. I erase the coordinate plane so that you see it better, you see the vector better. So right here there is no vector because Vy is 0 right here. Right here Vy is increasing because acceleration due to gravity at the y direction is negative 9.8, or sometimes we use negative 10. This is bigger and this is even bigger. Okay.